So actually, I mean, I probably misspoke when I said decimal. What you do is you take the binary representation of sine of 1 and then convert that to a hex string of 32 bits and use that as the constant string. I guess the representation is not important. Okay. You seed the Q values with the chaining value that comes into the hash function. You do your 64 steps, and then to finish, you add back in the initial chaining value to the final values you got. You append those together, and that's the output chaining value. Okay? So that's MD5's compression in a nutshell. It actually runs very, very quickly because all the things we're doing, like adding mod 2 to 32, shifting things, doing ands, ors, and nots, are all very efficiently done on a 32-bit processor, 64-bit processor. So this is a very fast function, even to do it 64 times for every message block you absorb. All right, so you probably didn't completely absorb all that. One way to synopsize is just say there are 4 rounds. Each round has 16 steps, total of 64 steps, and the step values are key to the attack, which is what we're going to talk about next. And they're called Q0 to Q63, and these are 32-bit values. Okay? So the properties of the step values are what matter for the attack. Now, recall that Wong's attack is aiming to produce 2 inputs, both of which are 1024 bits. That means M1 and M2, which are both 512-bit chunks, M1 prime and M2 prime. Okay, so as I said before, M1, M2 always differs from M1 prime, M2 prime in 6 exact bit positions. That's fixed. There's no playing with that. So we don't focus on M1, M2, and M1 prime, M2 prime. We focus on finding M1, M2, because from that you automatically flip those 6 bits and you've got the other one. Okay? So ignore the prime values. Those are automatically given to you once you have the unprimed values. Secondly, the attack for M1 is exactly the same as the attack for M2. It's just a different list of conditions that we have to satisfy. So the algorithm stays the same. So let's just focus only on M1. Let's just look at how to find M1. The same attack will apply to M2, to the second block. And you automatically get M1 prime from M1. You automatically get M2 prime from M2. Okay? So if you look at Wong's paper, it has these tables, these very intimidating looking tables with hundreds of characters with very specific values and so forth. And it takes a long time to extend, especially when she first published the attack, to figure out what these mean, because it wasn't really obvious at all. I'll tell you kind of at a high level what these tables mean. So here's the start of the table for the differential path, which is what's being described, for the first block attack on MD5. What it's saying is it's saying that in order to get a collision, you need, this first line says, on the third step, SI, the shift value, is going to be 22, and the difference, which is on the right-hand side, is a blank box. So there's still no difference. And that's because none of the message bytes with a flipped bit has yet been involved. As long as none of the flipped bits is involved, then you're not going to get any difference between the 2 hash functions. And this is telling you the difference on the step value between the hash on M1, versus the step value on the hash of M1 prime. So up to the third step, there's no difference. That's why the box is blank. Now, the next time on step 4, you'll see that there's the 5th column is delta W sub I. It's showing you that now one of the flipped bits is actually coming into play, 2 to the 31. That's the high bit of one of the words. And that causes the step value, Q sub 4, to be different in a bunch of places, namely in the 7th through the 22nd bit, and then minus 23 means it's actually a bit that's gone away. Okay? So there are these huge tables, and these tables keep tracking the difference in the step values between M1 and M1 prime, and that's what that right-hand column is doing all the way down. So what she's done is she's built a table which says if I vary M and M prime in a certain way, and then I compute MD5 in parallel in both of them, the difference between the intermediate values is going to vary by this much. Now it's down to here, now it's out to here. Now these bits are different, now these bits are different, and so forth. At the end of the table, if you're looking for a collision, what should be the difference? What should be the difference remember the step values eventually turn into the output, right? It should be another empty box. Now, it won't be for the M1, because remember, we get halfway there with M1, then we have to do M2. But at the end of the M2 table, finally, all those differences in the right-hand column evaporate to nothing, and you've got a collision. Where did these tables come from? We don't know. Even to this date, we don't know. Now, I talked to somebody who knows her fairly well, and apparently she dreamt them up. Did not use a computer to find these differentials. I cannot even begin to express how complicated it is to come up with something like this out of thin air. According to my friend Arjen Lenstra, who's talked quite extensively to Xiaoyun Wang, she has been sleeping with these hash functions under her pillow for 10 years. She knows the personality of Q7 bracket 15 intimately. She knows these hash functions better than she knows herself. I mean, this woman is, completely absorbed and consumed by these things until she finally broke them. So this is not something where somebody was just kind of a genius and walked up and went, oh yeah, here's a collision. This is somebody who's put 10 years of nonstop, tireless effort into these things and then burst onto the world scene. We don't know how to generate more of these tables. People have tried, and people have tried using computers to do it. And the best other differential paths that people have come up with for MD4 are still not as good as the ones she's done by hand. Okay, so still, like I just said, this is the only set of tables, the only differential path that is known for MD5. And all the collisions that we know of follow exactly this differential. And we now know many millions of collisions. If you just take two message blocks that differ by those 6 crucial bits, you're not going to get a collision with overwhelming probability. So what you do to do the attack is you pick any message block you like. And then you have to check for conditions. I'm running a little bit behind on time, so I'll probably start going a bit faster. 15 minutes left. So there's this long list of conditions that the step values all must satisfy. And for M1, there are 290 of them. And these are simple Boolean conditions like the bit here has to match the bit over there. This bit has to always be 0. This bit must be 1. This bit must be the opposite of that bit. Things like this. Things you can check very quickly.
Where did these conditions
They are also in the paper in a separate table.
So they're just...
Yes. So first you have the differential path. If you follow that path, you are guaranteed a collision. However, if you choose just 2 arbitrary messages that differ by those 6 bits, they're not going to follow the path. So now you start twiddling the bits to get them to follow the path.
But again, we don't know how she
The conditions are much more easy to understand the logic for. Once you have the differential path, you could say, all right, the tables immediately imply that that bit must be a 0 at that point. Otherwise, you will not follow this path. So you can do pretty simple inferences. And in fact, all the progress that's been made in speeding up these attacks, including the paper that I wrote, has to do with finding more conditions that can be easily satisfied. But nobody's figured out how to do other differential paths. That's completely opaque. No one understands how she did it, other than just by thinking them up. So she gave these conditions in the paper as well. 290 of them on the first block, 310 on the second block. And for the first round, first 16 steps, it's actually easy to satisfy almost all of the 290 conditions on the first block and 310 on the second block. And her techniques allow you to get all the way down such that there are only 37 remaining conditions on the first block and 30 remaining conditions on the second block. So if you can satisfy almost all these conditions very quickly in a deterministic way. So if you can't satisfy those last conditions and you need them, they are necessary. You need to satisfy them to follow the differential path. And if you let them just be randomly flipped, those last conditions, every condition is true or false, so it's a binary value. How many trials do you need if you're just randomly flipping 37 bits before they're all ones, they're all satisfied? You've got 37 true-false values, and they're all random. How many times? What are the odds that a 37-bit string chosen at random is all ones? 1 and 2 to the 37. And the expected number of trials, 2 to the 37. So it's about 2 to the 37 work before you actually get all of these conditions